In this subpart of the lecture number 7 of Physics 401A, we discuss the uniqueness properties of Lagrangian. Now let me start by giving you an easier example which you have already seen in the context of classical electrodynamics. Let us consider the magnetic field B, which has zero divergence. As it has a divergence is equal to 0, then magnetic field can also be written as can always be written as the curl of another vector, which is called A, or the vector potential of the magnetic field, right? Now, if someone writes, so curl of A is equal to B. Now, if someone writes another vector potential, which is basically equal to A plus gradient of another scalar function, let's say phi. Okay. Then curl of A plus gradient of phi will be equal to curl of A plus curl of gradient of phi. Now you all know that curl of a gradient is always 0, identically. Okay, it doesn't depend the specific properties or the specific expression or the specific functional form of phi. Okay, so it is understandable that whether you choose A or you choose A plus gradient of phi, finally the magnetic field which is derived from those two quantities are the same. Okay, so that's why we say that the magnetic field is unique here, but the choice of vector potential is not unique. So one vector potential can be differing from the other by the gradient of a scalar function. Okay. Here the question is the same type of thing, that does Lagrangian also have such type of uniqueness property? Such type of properties, so that if the Lagrangian is transformed to old Lagrangian plus something else, can that something else be such that finally the Euler-Lagrange equations, they stay unchanged? Or more precisely, the Lagrangian will be transformed to the old Lagrangian plus something, but the path of least action or the real path of the physical evolution will not be altered. How to find that? So here I said that we will be searching for additive transformations. Now if I just put more general comment, like saying that which type of transformation, additive, multiplicative, whatever, which type of transformation permits the Lagrangians, permits the Euler-Lagrange equation to be unchanged. Then of course one can understand from the very basic form of Euler-Lagrange equation that if we multiply the Lagrangian by an arbitrary constant, non-zero constant, let's say alpha, then of course alpha times L will also satisfy the Euler-Lagrange equation. Okay. So this is also a transformation of Lagrangian under which Euler-Lagrange equation stays unchanged. But if I tell you that, then it's also synonymous to say that when I multiply the Lagrangian by an arbitrary constant alpha, then the basic path, okay, of evolution, where for which the action, that means the integration L dt remains stationary, okay, will remain stationary before and after the transformation. Okay. Then it can sometimes be very, sometimes it seems that how is it possible? If I just multiply the Lagrangian, let's say by a constant 100, now then the action, which is integration over L dt, will also be multiplied by 100, right? So what we were saying, let's say the path of least action or the path of extremum action. So if it is, let's say it was a least action path, okay, then it will be simply multiplied by 100. Then there is no guarantee that it remains the path of the least action, right? My question to you is that think over this. Is it really so? What I am saying, is it really so? Think and answer it in the discussion forum, or I will discuss it in the discussion session. Okay. Because it is also true that if it is just multiplied by some arbitrary constant, then the variation of the new action is exactly equal to the variation of the old action. So if the old action's variation is 0, then the new action's variation is 0 as well. So what is going on? I mean, who is correct? Okay, so just think and try to answer me. However, here our aim is a bit different. We are searching for additive transformations, so that after the transformation, the new Lagrangian also gives us the path of least action or stationary action. So it is somehow just by observation or by investigation, it is found that if we transform the Lagrangian, or rather the old Lagrangian L, to a new Lagrangian L prime by this relation L prime is equal to L plus df dt. So remember, I mean, just notice this is not del f del t, this is df dt, or like f dot. Okay, that's the total time derivative df dt, where f is an arbitrary function of q and t. Okay, only it does not contain q dot, whereas L, both L and L prime, they contain q, q dot and t. Okay, if this is the case, then it is found that the Lagrangian, the new Lagrangian, will also give us the trajectory of least or the stationary action. How? So under this transformation, which I have just mentioned over here, we can write, so the new action after the transformation will be S prime, and that will be from T1 to T2 integration L prime dt, and that L prime is now integration T1 to T2 L dt plus integration T1 to T2 df dt times dt, right? So S prime will simply be equal to S, the old action, plus, so df dt times dt is nothing but df, and now this is integrated over T1 to T2, so it will simply be the function f itself evaluated at T2 minus the function itself evaluated at T1. So you can understand, as this is a function of q and t, so when it is evaluated at T2, the q will simply be the q of T2. Let me write that as q of Q2. Okay, and the same thing for this term. So this f will here, f is evaluated at time t is equal to T1 as a fixed time instant, and so the corresponding generalized coordinate will be Q1, which is the q at T1, right? Because I mean, should always remember that q is basically a function of t, right? Okay. Now we perform a variation of the new action. So delta S prime. Okay. So delta S prime, and we will check whether this is 0 or not. If this is 0, then the purpose is served. So delta S prime is equal to delta S. This is the old variation of the old action, plus delta F Q2 T2 minus delta F Q1 T1. Remember, so T2 and T1, they are fixed, so the delta operator simply does not move the time coordinates, but it simply moves the q's, right? So that if you really can remember, the smallness parameter epsilon changes. Okay, and this is nothing but the navigation from one trajectory to a neighboring trajectory, right? Now we know by definition at so t1 and t2, they are respectively the initial and the final time instance, and by definition we know that the variation is defined in such a way that at both t1 and t2 they should vanish. That means all the trajectories, possible trajectories, real and all the imaginary trajectories, they should coincide both at t1 and t2. Okay, then you can simply say this is 0, this term is 0, okay, and so for this term. Okay, so finally you can say that if delta s were 0, then delta s prime is also 0. Okay, now my question is, what happens if f is a function of q dot as well? Of course you can see that then this delta f would not simply be 0. So then we don't have this type of symmetry. Okay, think about it. If you are not clear about this, ask me. I will try to discuss this in the discussion session. Okay. Now, what is the meaning of that? The meaning is that under this transformation, the form of the equation of motion is unchanged. So if the Euler-Lagrange, both the old and the new Lagrangian, both of them are giving the path of least or the stationary action, then both of them will give the identical Euler-Lagrange equations. And of course, once you have the identical governing equations, then by solving that, the q of t which you finally find, okay, that will be unchanged. So the equation of motion will be unchanged and corresponding solution or all the states will be completely identical. Okay. Hence the Lagrangian, whenever this is defined, this is only defined to within an additive total time derivative of any function of coordinates and time, and that is known as the symmetry transformation of a Lagrangian. Okay, so basically another way of proving this type of, the symmetry transformation is directly you use this transformation in the Euler-Lagrange equation, and then by calculating finally the two terms of the new Euler-Lagrange equations, and to check that finally whether del L new or del L prime del Q is equal to ddt of del L prime del Q dot or not. Okay, if it is, of course you can show that they are equal. Okay, so that is the thing. Thank you very much.